Okay, 10.5 is about modeling exponential growth and decay. And so we spent some time graphing and looking at exponential functions earlier, and now what we're going to do is apply what we know about an exponential function to a real life applicative situation. And we're going to look at different ways that these types of functions actually exist in the world. So what you're going to need today is a calculator, and you can see I sort of have a little web browser calculator here. You can literally just open Google and type in scientific calculator, and you'll get a calculator like this. You can use your phone during the notes. You may need to turn it sideways in order to have some of the buttons that we're going to need to use for exponents, but it's just as easy to open up a web browser or to grab a calculator if you have one. So our essential question today, how do we model exponential growth and decay? So a lot of what's going to be happening in this section is that we're going to be learning and using different formulas and then applying those in the context of a word problem. So the key things to keep in mind are that you need to make sure you know what each variable is. Keep in mind, if we're talking about growth, then our final answer for each problem should be bigger than the original problem. If we're talking about decay, then the opposite should be true. And just really make sure you're understanding where the variables are coming from and in terms of the problem, like how we're picking out what each variable is and where that goes into each of the formulas. So our first formula is just the basic exponential growth formula. And exponential growth occurs when a quantity increases by the same rate, r, over a certain period of time, t. When this happens, we can use the formula in this box. And you're going to see, and I'm going to try and color coordinate here for us, that each of our variables, so y is the final amount that we have afterwards, and there's y in our formula, equals a. A is the original amount that we started with, times 1 plus r. And here's a really important thing about r. R needs to be represented as a decimal. So if you get a rate like 20% as a decimal, that means 0.2, right? You're moving the decimal place over 2 times to convert a percentage into a decimal rate. And then last but not least, we're going to be evaluating this at some sort of time. So y equals a, the original amount, times 1 plus r, our rate as a decimal, to the power of t. A couple of other things to consider. In almost every problem that we look at, we're going to be creating a model. And when I say a model, I mean a function. So when we're talking about a model, we're saying that we have a function where we can input a value for t and find a total value. For example, y, with the context of this problem. So whenever you have a model, you need to still have a t value in there. If you're using your model to approximate something, that's where you're going to plug in the number for t. So just be really cautious that you're not confusing those two things. So we're going to, for the first two problems here, write the exponential growth model for each situation, and then we're going to find the indicated value. So again, the model, I'm just going to make a little note to myself, this model should still have a t in it. So I know my model is eventually going to be y equals something times something to the power of t. Now I just need to figure out what goes where. So let's go ahead and read through this. A painting's original value would be the amount that we started with, is $9,000. So we actually just figured out what our A value is. Oh, let's try and make that a little bit more readable. We just figured out what our A value is. The value increases by 7% each year. So remember, we have to convert 7% into a decimal. So it's like I'm moving the decimal place 2 times. So 0.07 is our R value. The value increases by 7% each year. Find the value after 7 years. So after 15 years. We're not going to worry about that last sentence when we're creating our model. So 9,000 is going to go in front of our parentheses. Inside parentheses is 1 plus r, which in this case is 1 plus 0.07. So that's going to be 1.07. And it makes sense that this number inside is more than 1 because we're saying that this painting is increasing in value. If it was decreasing in value, then this number inside would be less than 1. So this is your model, and you stop here. You don't plug a number in for t. This is a function that we could use to find the value at 1 year or 5 years or 10 years or 50 years simply by plugging in a value for t. Now, when they ask us for a particular value, that's when we're going to plug in a number for t, and in this case, that number is going to be 15. So what we're going to do is we're going to say y equals 9,000 times 1.07 to the power of 15. And I want to see this step because if you make a mistake after this step, that lets me know that the mistake that you made was a calculator mistake, which we're hopefully going to prevent because I'm going to show you how to do this on a calculator. But I just want to make sure that I know that you knew where everything was supposed to get plugged in. And then our final answer, I'm just going to note to myself right now, is money. So I'm going to make sure I have a dollar sign here. And we're going to talk about how the fact that it's money also tells us where we should round. So let's look at plugging this in on a calculator. So, oops, I want to move my calculator. Okay, so the first thing I want to do, according to the order of operations, is deal with the inside of the parentheses, which is simplified. Then I want to deal with exponents. So 1.07, oops, not 1.7, 1.07. And then I'm looking for the exponent button. So since I need to go to the power of 15, I'm going to push this A to the B button to the power of 15. On a lot of calculators, that button looks like x to the y or y to the x. So 1.07 to the power of 15, I'm going to hit the enter button. So here I can see that 1.07 to the power of 15 is 2.759 and lots of numbers there. Now what I want to do is take that number, not round it, but take that number and multiply it by 9,000. So on most calculators, you can just, after you hit enter and you get this, you can just hit the button for multiplication and it will take the answer from the line before and multiply it by 9,000. On this particular calculator, I don't think it'll let me do that, so I think I need to hit enter and I need to push this button that says answer, which takes the button, or takes the answer that we just found above. The other thing is most of your calculators, if you're using a normal scientific calculator, if you push the second button and then the equal sign, that will usually take the answer from the line before. It'll usually say A and S in there as well. So I'm going to take the answer I just found and I'm going to multiply it by 9,000 and I'm going to get that answer. And so now I can see here is my answer. And this is a big increase in value here for this painting that we're looking at. Now we're talking about money. So when we're thinking about where to round, $24,831, we should only have 2 decimal places, so 28 cents. So 2 decimal places because we're talking about money. So again, when we're writing the model, we leave t in. When we're finding the model at a particular value, we plug that value in and we round in a way that makes sense for the particular problem that we're considering. Let's go ahead and look at the next question. All right, number 2, a sculpture is increasing. That's what tells us that we're talking about exponential growth, that word increasing here, at a rate of 8% per year. So we were just given our rate. 8% means that our rate is going to be 0.08. Remember, because 8%, we're going to move the decimal place 2 times. That gives us R is 0.08. Its value in 2000, that's the original value that we're talking about right now. So we just figured out that A is $1,200. Its value in 2000, in the year 2000, I guess that should say, was $1,200. Find the sculpture's value in 2006. So we don't need to worry about time yet because remember, right now we're writing a model. Our model should still have a t in it. So we're going to worry about our time when we get to the second part of this question. So we're plugging in front of parentheses the original amount. Inside parentheses, we're going to add 1 to that rate so that we get 1.08 is going to go inside our parentheses. So our model, y equals 1,200 times 1.08 to the power of t. Again, keeping the t in the model. Now we're going from 2000 to 2006, which means we're evaluating this when t is equal to 6. So we're going to be looking at y equals 1,200 times 1.08 to the power of 6. And then we're going to work that on our calculator, work that out on our calculator. So 1.08 to the power of, again, I'm pushing that A to the B button. It might be an X to the Y button. It might be a little up arrow, the caret button, like in English when you forgot a word in a paragraph, there's a little up arrow sort of looking button. To the power of 6. That's giving me this number, 1.586. Don't round it. Just take, now hit enter and multiply that by 1,200. Or in my case, I'm going to hit enter and push the A and S button and then multiply by 1,200 and get my answer. Again, this is money, so the way that I'm going to include units is by putting a dollar sign there, $1,904, and I want to include 2 decimal places. Since this is 0.249, I'm going to round that up to 25 cents. So $1,904.25 after 6 years. Seems like a pretty good investment. We maybe need to start investing in some art. Okay, let's go ahead and look at a different type of exponential growth, a very specific type called compound interest. So the type of interest that we just finished talking about is commonly known as simple interest or just basic exponential growth. What we're going to talk about now is something called compound interest, and this comes into play a lot with different types of bank accounts. And the basic idea behind compound interest is that you make interest off of your interest. So interest is money earned after a certain period of time that's contributed by the bank or wherever the investment is coming from. And with a simple interest account, you're never making money off of that amount. You're only ever making money off of the original amount that you put into the account. So what happens here is that with compound interest, we are earning interest. Interest is earned or paid on both the principal, aka the amount that you started with, and the previous amount of interest. So you make money off of the money that they gave you, which is kind of awesome. So the formula for compound interest at its core is a lot like the simple interest. It doesn't look like it, I know, but if this was a Y, if this was a Y, and this was an A, we still have something that looks like 1 plus R, we still have something to the power of T. The big difference here that's coming in is a slight change in variables, but also this N situation. That's definitely the thing that looks the most different, is what in the world is going on with these N's. So N basically is saying at certain points in time, we stop and recalculate the amount that's in the account so that you can earn interest off of the new amount in the account. So N is actually the number of times in a year that we are compounding that interest, the number of times in a year that we're compounding our interest. So if it happens annually, N would be 1, and we would actually just have the formula that we were just looking at before. If N is biannually, then that would mean twice a year, which would mean that N would be 2. If it's monthly, then N would be 12. If it's quarterly, then that would be 4 times a year. So N is the number of times that it is compounded. A is what we're actually looking for. How much money do we have at the end? P is the principal or the original amount that we're putting in. T is still time. And R is the interest rate, still expressed as a decimal place. So again, a lot of what's going in is the same. It's just different in the way, in the letters and how it's being put in. So the biggest difference here is really the N, which is the number of times each year that it is compounded. So let's work through a couple of example problems. Again, remembering that with the model, my final answer should be A times some stuff to the power of something times T. My model should still have a T in it. Okay, $1,200 is invested. So this is going to be my p-value, my original amount, which is going to go in front of parentheses, is invested at a rate of 2%, which remember we need to convert that rate into a decimal place. So R equals 0.02. And compounded quarterly, so there's our N value. Quarterly is going to mean that N equals 4. And we're going to ignore the 3 years part right now because we're just trying to figure out what our problem is or what our model is. So I know that I'm going to need N to be up here in the exponent. I also need to figure out just what is going to go inside these parentheses. So I should have 1 plus R, which is 0.02, over N, which is 4, to the power of 4t. So I need to simplify what's inside parentheses to finish off my model here. So let's hope this calculator is going to work with me. To simplify what's inside, I need to deal with the division first. So 0.02 divided by 4 is 0.005. Oops, I made it mad. And then we're going to add 1 to that. 0.005 plus 1. And that's going to give me 1.005. So that's what's going to go on the inside, 1.005. 1.005. So now I have my model. In order to evaluate that at the indicated time, I need to plug in t, which we are being told is 3 years. So A equals 1,200 times 1.005 to the 4 times 3. So I already have in my calculator this 1.005. So what I want to do is take that number, not round it, take that number and put it to the power of 12. 4 times 3 is 12. So to the power, that's my A to the B button of 12. That's going to give me a number, and I'm going to multiply that number by 1,200. So answer times 1,200. Now remember, if you're using a typical standard scientific calculator, you won't need to push that answer button as many times as I am. You should just be able to push the times, and it'll type in ANS for you. Okay, so that's giving me 1,274.013374. Where do we round? Well, we're talking about money here, so we're going to have 2 decimal places, $1,274.01. It should make sense that that number is bigger. We invested $1,200, and after 3 years, we gained $74.01 of interest, which actually doesn't really sound like that much, but it's probably more than you would get in a typical bank account of just regular interest. Okay, let's go ahead and look at one more example of compound interest before we start talking about exponential decay. All right, number 4, a $15,000 is invested at a rate of 4.8% compounded monthly. So the key word that lets us know that we're using compound interest is when it says the word compounded. If it doesn't say the word compounded, we're not looking at compound interest, we're looking at something else. So our principal, our original amount, $15,000 invested, our rate, 4.8%, which we need to convert to a decimal, and it's happening monthly, so that's going to give us our N value. So to start my model, I know I'm going to have A equals something to the power of something times T. Our original amount, 15,000. Our rate, if I move that decimal place twice, is 0.048. And if it's compounded monthly, that means that N is going to be 12 because there are 12 months in the year. So looking at this all together so that we can simplify what goes inside for our model, this is going to be 1 plus 0.048 over 12 to the power of 12t. So I can put a 12 right here in the exponent. But so what I need to do on my calculator is figure out what 0.048 divided by 12 is 0.004, and then I'm going to add 1 to that to get 1.004. And that is what's going to go inside here, 1.004. Then it's asking us to find the particular value after 2 years, which means we're going to plug 2 in, 15,000 times 1.004 to the power of 12 times 2, so to the power of 24. So I'm going to go back to my calculator. I'm going to take the answer that I just found. I'm going to raise it to the power of 24. Then I'm going to take that number and I'm going to multiply it by 15,000. And that's going to give me $16,508. Again, we're talking about dollars, so we should have 2 decimal places and 22 cents. So both exponential growth formula and the compound interest formula are both types of exponential functions or models that model growth, meaning we start with some initial amount and it increases. What we're going to spend the rest of this section of notes looking at is what happens when the opposite thing happens. What happens when we start with something and we actually decrease the amount that we have. And that's called exponential decay, and that's what we're going to look at next. Okay, so exponential decay occurs when the quantity decreases at some rate r over a period of time t. And this formula should look exactly like the exponential growth formula with one key difference. We are subtracting on the inside instead of adding because we are decreasing the amount that we have. Everything else about this model is the same. We're still talking about y being the final amount, a being the original amount, r being the rate as a decimal, and t being time. Everything else is exactly the same, except instead of adding our rate to 1, we're subtracting it from 1 because we're decreasing the original amount that was there. So let's look at this first example. The fish population in a local stream is decreasing. That's what tells us that we're using decay, this word decreasing here, at a rate of 3% per year. The original population was 48,000. So we have enough information just there now to write our model. We know that we want it to be y equals something times something to the power of t. The number that goes in front is going to be 48,000. Let's rewrite that. That looks better. And then to figure out what goes inside the parentheses, my rate is going to be as a decimal 0.03. And if we're doing 1 minus 0.03, we're going to get 0.97 inside. So there's our model. I can tell it's a model because there's a y and a t. Now we're going to evaluate that model after the indicated amount of time, which is 7 years. So find the value after 7 years means we're going to plug in 7. So 48,000 times 0.97 to the 7th. Let's grab our calculators. So we have 0.97 to the power of 7 equals, and then we're going to take that number and we're going to multiply it by 48,000. So here's something really important. We're talking about fish, and in the math world, we don't live in a world where there are partial fish. In the math world, things are perfect. So you are going to round down to the nearest fish. But you're going to round down. If I only have 0.17 of a fish, I don't have a whole other fish. So this is going to be 38,783 fish. 38,783. And don't forget the word fish because that is your units. So unlike when we were talking about money and we needed 2 decimal places, if we are talking about fish or people or some other sort of animal, we're going to round down to the nearest whole animal, item, person, whatever it may be. All right, one last type of model, which applies a lot in the sciences, is called half-life. So let's go ahead and look at the formula for half-life and learn how to model that. A common application of exponential decay is actually the idea of half-life. The half-life of a substance is the time that it takes for 1/2 of the substance to decay into something else. So here's the beautiful thing about half-life. You don't have to identify the rate because the rate is 1/2. That's why it's called half-life. So here is our half-life formula. And again, it looks really similar to some of the things we have talked about already. A is the final amount. Let's make that black. The final amount is equal to the original amount of whatever we're talking about. The difference here has a little bit to do with time. It's still to the power of t, but we have to divide t by the half-life time. And that will be specifically given to you in each problem that involves half-life. So again, when we see the word compounded, we know we're talking about compound interest. When we see the term half-life, we know we're talking about half-life. In any other situation, we're assuming that we're talking about standard exponential growth or decay, depending on the situation. So just like on the other examples, we're going to write a model, and then we're going to find the value of the model at a particular time. And the time is usually the part that people struggle with a little bit here. So we know that we're going to have our model say A equals, and in every half-life problem we're going to have 0.5, and we're still going to have a t. We just need to figure out what t is over. So number 6, acetane 218, which is an element, has a half-life of 2 seconds. Find the amount left from a 500-gram sample, so that's our original amount, after 10 seconds. So this is the time that has passed. The other time is the half-life specific time. It has a half-life of 2 seconds. So that part is H. That's going to go here. And there's nothing to simplify. Remember, you can't multiply 500 times 0.5. That would violate the order of operations. You are officially done with your model. And then to evaluate your model, I'm actually going to come down below here because there's a little bit more space. To evaluate our model, we're going to plug in the amount of time that they told us has passed, which is 10 seconds. You need to make sure both of your units are the same. So these are both in seconds, so that's fine. I can leave it just like that. This is going to give me 500 times 0.5 to the 5th power. And I can do this part on my calculator, 0.5 to the 5th power, and then multiply that by 500. And that gives us 15.625. If a problem doesn't specifically tell you where to round, I don't want you to round. So there's only 3 decimal places. You're going to write all 3 of those decimal places here, 15.625. So the answer is 15.625, and we are talking about units in terms of grams, 15-gram sample. Why don't you go ahead and pause the video and try and write out the model for number 7 all on your own, and then unpause the video and see how you did. Okay, cesium-137 has a half-life of 30 years. So that's our H value. That's going to go underneath T. Find the amount left from a 100 milligram, so I know my units are going to be milligram, 100 milligram sample after 180 years. So my model is going to be A equals 100 times 0.5 to the power of T over 30. To evaluate that, we're going to say 100 times 0.5, and it says we're evaluating this after 180 years. So 180 divided by 30, so 100 times 0.5 to the 6th power. So we're going to do that on a calculator, 0.5 to the 6th power, and then multiply that by 100. So that's going to give us 1.5625. Again, don't round. The problem didn't tell us where to round, so it's safer just not to. So 1.5625 milligrams, and again, we're not rounding there. So big ideas in this section. We learned 4 different models of exponential functions. 2 of them involved growth, simple compound growth, or simple growth, compound growth, and then 2 involved decay, exponential decay formula, half-life formula. Some things to remember, the places that people usually make mistakes. Remember that a model will always have 2 variables, which means every single time we wrote a model, there was an A or a Y equals, and there was still a T in the specific function. The reason being, we want to be able to substitute in any T value that we want to find a specific value. Round according to the context of the problem unless otherwise specified, and if it doesn't specify, don't round. Write down all of the numbers that you see on your calculator. And don't forget units, whether it's grams, a $sign in the front, the word fish, whatever it may be, make sure that you don't forget units. So go ahead and write down any questions you have. I look forward to supporting you on this in class. Thanks for listening.